Students of M.Sc Chemistry from Semester 1 of Physical Chemistry and respected listener, a very good afternoon and welcome all of you to today's lecture. Students of M.Sc Chemistry from Semester 1 of Physical Chemistry, I am going to present today a very special new topic titled I have mentioned on the blackboard, which is known as that is of activated complex theory, which is also called as that is of a transition state theory, absolute reaction rate theory, which is selected from that is of M.Sc Chemistry from semester 1 of paper 3 physical chemistry, chosen from that is of a unit 3rd titled as that is of a chemical dynamics. Once again, students of M.Sc Chemistry from semester 1, I am going to deliver to you today a very special lecture titled I have mentioned blackboard. Once again, the title I repeat once again, activated complex theory, which is also known as that is of transition state theory and absolute reaction rate theory. Today's lecture is very outstanding and important for various competitive examination based at the level of M.Sc Chemistry, and that is the best at the level of unit 3rd title, and that is a chemical dynamics here. Before to deliver today's lecture, before proceedings of today's lecture, activated complex theory or transition state theory or absolute reaction rate theory, once again I would like to focus some about to describe, to repeat our important postulates of our last video based on that is of chemical dynamics. Today that is of collision theory and that is of drawback, limitations, failure and need of modified collision theory. First of all, I repeat about some important postulates of that is of collision theory, in which collision theory is depending upon in which we have to calculate two types of the velocity. First types of the velocity of the reaction, which will be calculated by using that is of collision theory, in which calculation of velocity of the reaction is depending upon two types of the factors. First types of the factors in which is expressed by that is of ZAB to define as that is of per centimeter cube per second number of active or that is activated collisions of reacting or species reacting molecules of A and B, which is symbolized by that is of ZAB. Second one, the calculation of velocity of the reaction is also responsible upon the area of activated reacting or colliding molecules, which is measured in terms of that is of e to the power minus e upon RT here. When we multiply that is of collision coefficient ZAB with that is of activated that is of surface area of the reacting or colliding molecules e to the power minus e upon RT, which is also known as that is of partial RNS equation to give the value of velocity of the reaction according to that is of a collision theory. The calculation of velocity of the reaction is calculated, is observed under two important conditions. First one, when the reacting species are present in different concentration and different nature, and their behavior to act as that is of rigid dynamic hard sphere here. Next one, the same velocity of the reaction now is calculated with that is of a normal that is of a chemical dynamics you have studied at the level of basic part 1 using that is of law of mass action or Goodwin or Vargas law to give the value of dx by dt velocity of the reaction. According to the law of mass action, for performing of any that is of a second order of reaction, velocity or rate of the reaction is directly doubly power of initial concentration, which is present in terms of, which is measured in terms of doubly power of active mass here. When we compare both of the velocity of the reaction observed by that is of collision theory, second one derived by that is of simple collision theory, and by the cancellation of Na and Mb, which denote here the different dense concentration of earlier to which we are using the earlier that is of reactant A and B. Now after the that is of when we apply the various mathematical that is of treatment operation steps and followed by a temperature condition here. Finally, in our last video we derived equation number that is of 14 to give first types of the amazing marvelous equation to define to calculate the value of velocity of the reactions here, and is also known as that is of RNS equation. Under second condition, to define about that is of collision theory, it is also possible to take the same reacting species, reacting molecules in terms of that is of A, and in such a position the collision factors, the collision coefficient ZAB is now replaced by that is of ZAA, which is defined in per second per centimeter cube number of active or activated reacting or colliding molecules. Again is now again multiplied with that is of activated surface area, which is also multiplied to give the value of E to the power minus E upon RT. Now again we compare the velocity of the reaction under that is of a second case, and we now compared with that is of a velocity of the reaction now calculated by that is a simple that is of a chemical dynamics method. After the cancellation, the various in our last video we have calculated the value of that is of equation number 16a, 16b, 16c to give the difference form of the RNS equation to calculate the value of velocity of the reactions here. Now, although the collision theory basically give us the necessarily fundamental equation for the progress of various chemical dynamics, chemical reactions, although in collision theory to have to possess some that is of drawback, limitations, failure, and let us try to understand various that is of drawback according to that is of point wise. First one postulate to define that is of weakness, limitation, or drawback that is of collision theory. The derivation of velocity constant and velocity of the reaction is fully based upon that is of kinetic, ideal kinetic molecular theory of the gases here. Why other states of the matter, liquids, solids have not been that is of included to derive that is of necessarily derivation equation number 14 and equation number 16. It was the first drawback or limitation of that is of collision theory. Second one, for the derivation of expression of equation number 14 and equation number 16a, 16b, 16c. The behavior, the nature of the reacting species A and B have been assumed to behave to act just like that is a rigid dynamic hard sphere. Why particularly that is of dynamic behavior of the colliding molecules have been involved. So about the information, this collision theory exactly doesn't give to explain about the necessarily fundamental equations here, explanation here. Next one, third one, in order it is particularly applicable for very simple bimolecular application to give the value of velocity constant calculated by that is mathematically and that is of practically to give to possess the same value. K theoretical is equals to that is of K practical here. I mean to say collision theory basically explained to give the value of that is of simple bimolecular gaseous reaction, that is treatment of nitrogen and oxygen to produce nitric oxide, and treatment of hydrogen and iodine to produce that is of twice mole of HI. These are the very simple bimolecular gaseous reaction to calculate to give collision theory the necessarily and to define dynamic process in that is of exact way to give the value of K theoretical is equals to that is of K practical, as we have derived from equation number 14 and equation number 16, our last equation here. But in the case of some typical reactions, it doesn't explain about that is of necessarily fundamental equation exactly to give that is of doesn't explain the kinetics of some important typical reactions, or in such a reaction some typical reactions undergo present in that is a chemically that is of reaction undergoing here. For example, some important typical reaction bulk typical reacting molecules present, such as that is of polymerization of ethylene, polymerization of 1,3-butadiene, that is of bulk and that is of dense reaction and treatment between that is of ethyl alcohol with that is of acetic anhydride. These are the such typical reactions in which when we calculate the value of velocity constant from equation number 40 in our previous video, so obviously K theoretical will not be is equals to the value that is of K practical here. So obviously about this information collision theory doesn't explain about that is of its logically. Also, next one, failure of that is the collision theory. I would like to explain to you among the students here. Basically, the calculation of velocity constant of our last equation number 14 is basically applicable for such a simple bimolecular reacting molecule here, in which two passes that is of a single degree of freedom here, either two passes that is of a translational degree of freedom here, rotational degree of freedom here, or vibrational that is of degree of freedom here. I mean to say it is applicable for such simple bimolecular gaseous reaction to have to possess only a single that is of degree of freedom here, either to possess that is of translation degree of freedom or vibrational degree of freedom, or that is of translation or vibrational, either that is of rotational degree of freedom. It will give to calculate the value of K theoretical will be equal to that is of a K practical is equal to here to proceed here. Now, but for dense or bulk or some typical reactions undergo to possess the three types of the degree of freedom at a time, translational, rotational and vibrational, to occur simultaneously when we calculate the value of velocity constant from equation number 14. So obviously theoretical and practical value to give the different value. I mean to say theoretical will be equal to that is the practical value here. Also, it is the next one, failure or weakness of collision theory here. Now next one, using it is for such fast reactions, chain reactions, treatment of between that is of H2 and Cl2, St and Br2, chain reaction, fast reaction. The velocity constant calculated from that is of equation number 14. Much higher deviation 10 to the power minus 4 is now observed here. It is the next one that is of drawback here. I mean to say for fast reaction K theoretical will not be equal to that is of K practical here. Next one, drawback, particular energy of activations for proceeding of the reaction for performing of to produce that is a product, a particular kinds of the reactions here. I mean to say that is of energy of activation is considered here, while other kinds of that is of energy regarding to that is of thermodynamic, such as Gibbs free energy G, Helmholtz free energy A, entropy that is of H, S, and entropy that is of H, internal energy that is of U and E. Regarding these various kinds of the thermodynamic kinds of energy, while the deriving of the necessary derivation, these various kinds of the energy have not been that is of involved here. Next one, postulate defined to that is of drawback or limitations. It explains about that is of initial and final state, and it doesn't explain about the position of the reacting or colliding molecule in terms of that is of in transition state. Also, what is the role of the reacting species in mid to cross a particular barrier here. So I mean to say, students of M.Sc chemistry for semester 1, these are the various important drawback failure to need to define that is of modified collision theory. In order to remove these various drawback and limitations, now we introduce a new important factor in general simple collision theory, equation number 16, to multiply to that is of involve that is of to introduce that is of next one P, which is known as that is of probability factor. K is equals to P into that is of Z e to the power minus E upon RT, where equation number 17 is known as that is of modified collision theory, where P one can define denotes here that is of probability factor, steric factor, or that is of activational entropy. It defines and equation number 16, K is equals to, where K denotes that is the velocity constant here. For second order of reaction, K is equals to Z to define in terms of that is of a collision coefficient to collision that is of factors here. E to the power here, you know, e to the power minus E upon RT, this one, e to the power minus E upon RT to define the surface area in mathematical form in terms of that is a partial that is of RNS equation. Now when we introduce that is of next one P probability factor, which is define the 3D geometry structure for typical reactions here. So I mean to say equation number 70 is known as that is a modified collision theory. Now let us try to understand today's the next new topic, that is a transition state theory, which is also known as that is of activated complex theory or absolute reaction rate theory. So first of all, some postulate I would like to define here according to that is of a point wise here. The above theory developed by Eyring, that is of Polanyi and Evans in 1935. First postulate to define about activated complex theory. The theory developed by Eyring, Polanyi and Evans 1935, and the last postulate the derivation of activated complex theory can be derived by using two important equation here. First one I choose here A plus B. A plus B denote here that is a normal, that is a molecules here, and after collision A plus B now that is converted into the next state which is known as that is active molecules here, and by means of first types of the that is of constant here K star to convert that is activated complex theory, and by the decomposition of next one K or K2 now convert into that is of P. Now we consider here by considering a specific example a hydrogen molecule to act as that is of A, and next one chlorine molecule to act that is of B, and by means of first types of the constant here K to convert into the activated complex here, and by presence of by means of next constant K or K2 P to convert that is of 2. Next one equation number 2. So by the consideration by the assumption of two types of the reacting species here to form intermediate complex here, and by means of first types of the constant symbolized by that is of K star, and next one activated complex which is present the concentration in terms of that is of active mass, and next one by means of second the presence of a constant K or K2 it now convert into that is of a final product here. So obviously these were the important postulates to define activated complex theory, transition state theory, absolute reaction theory defined by that is of Eyring, Polanyi and Evans in 1935, and by means of the collisions of earlier we have assumed the reacting species A and B to consider as a normal after the collision to proceed in terms of active molecules. These active molecules with recombine again that is to produce by the combination of within direct contact or to produce new types of the species which is nowadays that is of activated complex and symbolized by that is of star. Rest the production of the formation of product depending upon only on the that is of excess concentration or bulk concentration activated complex which is symbolized by the that is of a star. The detailed theory about activated complex I will teach you in tomorrow. Now let me allow to me to join to you that is of tomorrow's lecture. Now you take care yourself. Goodbye. Thank you very much.